You guys, what is the electric field within the substance of a conductor?
Zero.
Wrong. Now, that's what I was trying to get you guys to say. Now, it is true that it's zero inside a conductor if the conductor is in electrostatic equilibrium. Every conductor in a circuit that's connected to a voltage source is not in electrostatic equilibrium. So, for example, in my battery that I've got right here, in this conductor, right here, there is electrons flowing. There is an electric field. And these arrows represent those electric fields. There is an electric field inside the conductor because charges are moving. It is not an electrostatic equilibrium. You can have an electric field in a conductor, and that just means that charges will be moving. And they'll keep moving until the field is zero, which will never happen until this battery runs out of chemical energy. So what we need to do is we need a microscopic model to figure out what's going on. So our microscopic model, here is what is involved. We have got a couple of important numbers here. One is little n. Little n is the charge carrier density. It is the number of charges per unit volume. So that is just going to be a number per cubic meter. And is the number of charge carriers. You guys, what is the actual charge carrier in a conducting metal? Electrons. So basically, if you knew how many atoms there were and you know how many free electrons there were, you can figure out the number of charge carriers, and using the density of the metal, you can figure out how much volume it would be per a certain number of atoms. So little n is the number of charge carriers per unit volume per cubic meter. Volume of a section of wire, this has area A, cross-sectional area A, and I'm going to be examining a length delta x. The volume of that section is simply A times delta x. Are we in agreement on that? And the other thing you need is the drift velocity of electrons. Drift velocity, and we call it VD, V sub D, is the average velocity of charge carriers that go down a wire. Now, I'm going to give you three choices, and I want you to guess which would be in a common 12-volt circuit that you might find in your car. Which one of these would you expect to be the actual drift velocity, the average velocity of electrons? Choice 1 is 1,000,000 meters per second. Choice 2 is 1 meter per second. Choice 3 is, let's say, 1/10 of a millimeter per second. Which one of those would be the drift velocity of an electron in a wire in a 12-volt DC circuit? Now, if you guess 1/10 of a millimeter per second, you'd be right. 1/10 of a millimeter per second? How is it possible that I turn on that light, boom, and the lights over here go on instantly or almost instantly? The electrons do not drift very fast. What actually moves very fast? The charge does not move very fast. It moves at 0.1 millimeters per second. What does move fast? The electric field moves at almost the speed of light. And what that does is that will push the initial electrons, and then it will really pull them. Very quickly, it's pulling the electrons at the very other end of the wire. So it's the electric field that moves fast. The drift velocity is actually very, very slow. It's not even a millimeter per second. It can take hours for one individual electron to get from the negative terminal of a battery to the positive terminal through the circuit. It could take hours for that to happen. But that doesn't mean the signal travels very quick, close to the speed of light. Now, to figure out the number of charge carriers in any section of wire like this section right here, all you got to do is multiply the number of charge carriers per unit volume times by the volume. So that gives you the number of charge carriers. Now, charges go from here to there in some time delta t. The distance that they travel is the drift velocity, again very slow, times delta t. Now, this symbol E, that's what we use for the elementary charge. The charge of an electron, what we call the elementary charge, is 1.6 times 10 to the negative 19 coulombs. That's a very, very small amount of charge. It's 1 electron charge. That is the charge carrier charge, E. The total charge that exists in this part right here, the total amount of charge, delta Q, is equal to the charge carrier density times the volume times the charge of the electron, or of whatever your charge carrier is. That is the total delta Q. The number of charges times the charge of each one. So to figure out the current, all you got to do is take that total amount of charge, which is the number of charge carriers per unit volume, times the area, times the delta X. Notice that what I'm going to do is, delta X is V drift times delta T. So when I divide this by delta T, what I get is this. Now, what the mnemonic is for this is the average current. If you just remember this cool mnemonic, and instead of drift velocity, I'm just going to put velocity. Well, I never. That is the current based on the charge carrier density, charge per unit volume, the charge of one charge carrier times its velocity. There is a little d here for drift velocity. Well, I nevda, but I never sounds funnier. Well, I never. That's what, yeah, I'm never going to learn this. This is your current in terms of all those variables. Well, I never. Sweet.